My name is Rich Bleil. You have asked me to do a demonstration of my teaching ability on some topic of relevance. I'm a theoretical chemist. That puts my training in mathematics, chemistry, and physics somewhere in that mix with a lot of computer science as well. For my teaching demonstration, I've decided to talk a little bit about entropy and the second law of thermodynamics because I feel like it is, first of all, the least well understood law of thermodynamics. It is also probably one of the most applicable laws of thermodynamics, especially for a technical college and for everyday life, truth be told. At this point, the students would have heard about, we would have discussed the first law of thermodynamics, the law of conservation of energy, and the fact that energy is naturally tends towards lower energy levels. For example, yesterday I ate an apple, and right now the apple core is in my garbage, decomposing. As it's decomposing, it is naturally going to lower and lower energy levels as the sugars are breaking down, the proteins are breaking down, and it's becoming lower energy. There are two driving forces in the world. One of them is the first law of thermodynamics, the fact that energy always tends towards lower values. The second law of thermodynamics is the second driving force in the universe. That is the law of entropy, where entropy tends to constantly be increasing. And those are the two kind of opposing forces in the universe. Entropy is always given the symbol S. And the change in entropy is always, the formula is delta S is always greater than or equal to delta Q over T, where S I already mentioned is entropy. Q is heat, and T, of course, is temperature. A lot of people think that they understand the second law of thermodynamics. They believe that the second law of thermodynamics says that entropy can never decrease. This is wrong. If entropy could never decrease, we would not be alive today. The most entropic form of water is actually water vapor. Today they are predicting thunderstorms here in Iowa. If entropy could never decrease, water, once it evaporated, would never be able to recondense back into liquid or solid form. It would never precipitate. There would be no water to drink. We would be dead. What the second law of thermodynamics actually says is that entropy for the universe can never decrease. In my class, I would have already discussed the fact or the idea of the system, the universe, and the surroundings. A system is very easy. In fact, what I have here set up is a demonstration on the system. This system is obvious. This is a little container of water, and this is my favorite demonstration of entropy. Nothing really surprising is going to happen here. This is the ink drop demonstration. And all I'm going to do is squeeze a drop of ink, first of all, onto the paper towel there. That's entropy as well. I'm going to squeeze a drop of ink into the water, and we're going to watch it. There's nothing surprising happening here. I think it's a beautiful demonstration. It's fun to watch. The entropy, the ink has kind of distributed itself on top of the water, where just kind of surface tension caused it to spread out. The ink is a little bit heavier than the water, a little more dense than the water, so it is falling to the bottom. And we can see where the ink is falling, and we can watch sort of the beautiful ballet that ensues. We know that this ink is going to distribute evenly throughout the water. One of my favorite tongue-in-cheek definitions of entropy is if you put a drop of wine into a barrel full of sewage, you get a barrel full of sewage. But if you drop a drop of sewage into a barrel full of wine, you get a barrel full of sewage. This is a silly definition, but it's kind of true. If we knew where that drop of sewage would end up, we could take that portion of wine out of the barrel and we'd have drinkable wine again. But we don't. We know that that sewage is going to disperse throughout the entire barrel, just like we know that this ink is going to disperse throughout the entire glass of water. That driving force is entropy. And that is one of the natural driving forces, one of the two, for everything. Now, the thing about entropy, it can decrease. We can separate this ink out from this water again. If we distill the water, we would get pure water again. So we know that entropy for a system can decrease. And here the system is obvious. The system is the container of water. The surroundings is everything around the container of water. When you add the system and the surroundings together, you get the universe. This is something that I would have discussed already to my class. That the system plus the surroundings is the universe. The second law of thermodynamics tells us that the surroundings of the universe can never decrease. But the entropy of the universe can never decrease. But the entropy of the system most definitely can. For example, and this is sort of from everyday life, and we know this. Suppose that we are driving along. It's a beautiful day out, if I can get my pen to work again. And here's our road. We're driving down the road. And the sun is out, and it's shining, and it's just lovely. What happens over time to the road? Well, we know, and this is a common Facebook meme that occurs around this time. The state flower is the construction cones, and everywhere everywhere people live, they have the same joke. Why is that? Think about the road. What we have done is we've put a lot of work into the road to create essentially one long continuous rock. That's what a road is. That's what cement is. That's what asphalt is. But over time, what are we going to get? We're going to get potholes. And the road is going to begin to crack, and we may get some sort of dirt or debris on the road. This is entropy. This is the natural process. The natural process is for the road to fall apart to a road. So now, and this is kind of an interesting thing, you know, systems are not always defined to tiny little beakers or cups or flasks. We can define the system to be as large as we like. The road is now our system. That's it. It's not contained to one container. It's a much larger system than that. But the second law of thermodynamics still applies. How do we decrease? Now, here the entropy of the road is increasing. How do we decrease the entropy of the road? Well, eventually we're going to go and we're going to fill in our cracks and our potholes. We're going to sweep off the debris or pick it up. We can decrease the entropy of the road. We may even have to take the road up, put it back down again sometimes. That just happens. How do you decrease the entropy of a system? You do it by doing work on the system. Just like here, if we distilled this container, we would be doing work on the system. We would be decreasing its entropy. And as we're doing that, how do we increase the entropy of the surroundings? I mean, we have this road. We're filling it in. How does that increase the entropy of the surroundings? Because we know from the second law, the entropy of the surroundings have to increase at least as much as the entropy of the system decreases. It can never be the net entropy of the universe. The best we can hope for is neutral, and it never happens. Well, think about what we have to do to decrease the entropy of the road. We're going to use heavy equipment, burns fossil fuels, takes all of those liquids from oil and gasoline and converts them into carbon dioxide. They're going from the liquid state to the gaseous state. That's a huge increase in entropy. Even if we did it by hand, then our bodies would be burning sugar in order to do the work on the system. And that's converting the sugar into carbon dioxide and gases. So by doing work on the system, yes, we can decrease the entropy of the system, but we're increasing the entropy of the surroundings. That's the cost of repairing the roads, is the entropy to the surroundings. If you add the amount of entropy increase from the surroundings to the amount of entropy decrease from the system, we will find that the surroundings will increase more than the entropy decrease of the system. Normally at this time, I would start talking about calculations, and I would show how to actually calculate these numbers for the class. But since this is a demonstration and you wanted it to be between 10 and 15 minutes, I think I'm going to stop here. I would like to thank you for your attention and time, and I look forward to talking with you all in the near future. Thank you very much for your attention. I'm going to turn the system off now, and I hope you have a great day.